Thanks for the introduction and for the opportunity to present our work. So I'm Jérémy Briant, PhD student at CNRS in France, and I'm currently working with IRIT and Cerfacs. And I'll talk about background error covariance matrix estimation using multifidelity ensembles. So I'll talk a bit about the context of our work, then present the method we used, the multilevel Monte Carlo, then our numerical test case, the corresponding results, and I'll conclude the talk. So first, in many geophysical data assimilation problem, the estimation of B, the background error covariance matrix, is crucial, and this matrix is estimated using ensembles. The problem is that the problem size can be very large, and so generating members can be very expensive. So usually it leads to small ensemble size, like 10 or 20 members, and thus high sampling error. Usually this matrix B is estimated using the Monte Carlo method with the formula displayed here. So the estimator B tilde with capital N members, and eta is a perturbation. So this is what is usually used. And just a little visualization of this problem. Here you can see Monte Carlo estimators of matrix B true, and you can see that with small ensemble size, like 10 members, we are very far from the truth matrix. So what is commonly used to measure the accuracy of an estimator is the mean square error, which admits a nice decomposition in two terms, the sampling error and the bias. The focus of our work is on the sampling error. You can reduce it, of course, by increasing the ensemble size, but it's very costly. So the other way is to use a variance reduction technique, like the localization, which is very used in data assimilation, or the method we will present, the multilevel Monte Carlo, MLMC. So as I said, our objective is to reduce the sampling error of the estimation of a matrix B given a certain budget by using the multilevel Monte Carlo methods. And just quickly, here are three references. The first from Giles present the multilevel Monte Carlo methods. The second one from Ehouarn and al. Is an application of MLMC to data assimilation, but it's very different from our work since they don't estimate covariance matrix. And the last one is about estimation of covariance, but not in data assimilation. So let's go on to the presentation of the multilevel Monte Carlo estimator. So first, let's suppose we have different fidelity ensembles. The different fidelity ensembles can be obtained by reducing the time resolution of your model or reducing the space resolution. It can even be by using double precision or single precision digits. And so the MLMC estimator is basically an estimator on the coarser and cheaper level, the level 0. And then you add a succession of corrections up to the finest level you have, the level capital L. A nice property of this estimator is this telescopic expectation sum. So as you can see, the expectation of our estimator is the expectation on the finest fidelity level. So it means that by adding a coarser fidelity level, we don't deteriorate the bias of the estimator, which is a nice property. But as I said, the focus of our work is on the sampling error. So we want a variance reduction. So here as a variance decomposition, I used only a coefficient of the matrix B to be more clear and concise. What is important with this decomposition is this upper bound with what we call VL, which are constants that are independent from the number of members. And we'll use those VL to check the effectiveness of the MLMC. And so to have a variance reduction, we can expect to have this variance reduction by having a large ensemble size on the coarser and cheaper level. And we can also expect to have a smaller and smaller ensemble size as level increase. So on the finest level, you can expect to have a small ensemble size, since the variance of the correction will decrease. And so here at the bottom of the slide, you can see the decomposition of the variance of the correction. And what is interesting in this decomposition is the last term in red. We want to have this term as high as possible to reduce the variance. So we need to have correlation between levels. It's a key point of the effectiveness of the MLMC, so keep that in mind. And to illustrate a bit what I'm talking about, here you can see the variance reduction we can expect for a two-level multi-level Monte Carlo. On the y-axis, you have the cost ratio between your two fidelity level. So, for example, if you imagine that you are reducing the space resolution by 2 in the 2 direction, and you also reduce the time resolution by 2, you can expect a cost reduction of 8. So you'll be around this part. And with the corresponding variance ratio, you can be in the green part and expect to have a variance reduction. And the variance reduction can be increased with the number of levels available. So just to summarize a bit the multi-level Monte Carlo estimator, if you have a fixed number of levels of different fidelities, then if those levels are more and more accurate and also more and more costly, and if the VL, so the variance of the correction, are decreasing along with L increases, then you can expect to have a variance reduction compared to a standard Monte Carlo method for a given budget, thanks to an optimal allocation of the members in the different fidelity level, thanks to an explicit formula that can be found in the reference here. So now, to illustrate this estimator, I will present the numerical test case used. We wanted to evaluate the performance of MLMC first in a model-free context. So we are generating ensemble members from a matrix B true that you can see on the left of the slide. So basically, we are generating uncorrelated noise, epsilon, and we can obtain the corresponding perturbation by using a diffusion operator. And we have the different members that will be used to estimate the matrix B, for example, with Monte Carlo. That will be the comparison we used in the following. So to use MLMC multi-level Monte Carlo in this numerical test case, we need different fidelity level. We simply did that by restricting the noise and grids of lower and lower resolution. In our case, we had 4 levels. So the finest one had a grid of size 64, and we can restrict the noise on a coarser grid size 32, and same for 16 and 8. And we choose a restriction to keep the property of the uncorrelated noise. So that's our different fidelity levels. And as I said previously, a key point of the MLMC is to have correlated numbers, compute the correction terms. So to obtain those correlated numbers, what we did was generating an uncorrelated noise on the finest level. So we call this noise epsilon capital L. We can obtain, of course, the corresponding perturbation eta capital L. But we can also restrict this noise on a coarser level and then obtain the perturbation. And those two members that are on a different fidelity level are correlated since they come from the same uncorrelated noise. So in a real application, you can it can be the equivalent of generating members with the same initial condition or the same perturb observation to have correlated members. Then just quickly about the budget, the fixed budget of our MLMC. We fixed the cost of generating one sample on a finest level at 1, and we had a cost ratio of 8. So basically generating one member on the finest grid is the same cost as generating 512 members on the coarsest level. So onto the results of our test case. First, in red, you can see what we call the VL, the variance of the correction terms. And they are indeed decreasing with the levels. So we can expect to have more members on the cheaper and coarser level, the level 0, and less members as the level increase. And in fact, in blue, you can see members allocation for a budget of 50. So instead of generating 50 samples on the finest fidelity level, we have more than 1,000 members on the cheaper and coarser level. Just note that to obtain this optimal allocation of members, you need to have the values of the VL, which implies estimating the fourth order moment element-wise of the perturbation. But it may not be such a problem. And so to compare our MLMC, the MLMC estimator with the standard Monte Carlo estimator, in red, you can see the standard Monte Carlo estimator, and you can see that its variance is decreasing along with the available cost. With more available cost, there will be more members. And in green, the MLMC estimator, which follow the same pattern, but with a variance reduction factor of more than 5. This factor can be increased with the number of levels available. So to conclude, what we did was illustrating the MLMC on a model-free context, but we foresee some open questions on more complex application. For example, we can't guarantee that our estimator will be positive semi-definite, which can be a problem. We also don't have a direct access to the decomposition of B. As I said, the key point of MLMC is to create correlated members, which may not be as easy as it seems. And so what we are planning to do is to investigate, of course, the above point, maybe by applying MLMC to more complex models. And we are also planning on doing a spectral analysis of MLMC and maybe investigate some links with multi-grid methods. And finally, we are also thinking about combining MLMC and a localization method for further variance reduction. So thanks for your attention. Here are the references I mentioned in the talk.
Thank you, Jérémy, for very nice presentations. We already have some question from Petayan. So he's asking, a problem with multi-resolution methods in weather forecasting is that different resolutions have different physics. So the correlation structures can be very different between levels. Do you have ideas on this, or is this not a problem that is relevant in real applications?
In fact, it is a relevant problem, and we are thinking about weather forecasting applications. And we know that by having different fidelity resolution, we have different models. We are thinking about it, and what we just need to have is having the correlation between the members, like here, between the different fidelity levels. I don't know how it will go, but yes, we are thinking about that, and just need to have the correlation between the different fidelity level, even if they are different, completely different models.
Thank you, Jérémy. So basically, is it that you're saying that you need these levels somehow to be close to each other? So let's say I have a resolution of a 3-kilometer model, then I would, I don't know, go 6 kilometers, 10 kilometers, or should I go 20, 40, and so on? So do you need them to be like really, do you need these cross correlations to be strong, or do you need them to be very weak?
We need them to be as correlated as possible, so it may be better if the difference of the space resolution, for example, is not very high between the different fidelity levels. Mm-hmm. But I don't know much about the different models, so I don't have any idea of how much we will need between different models.
Okay, thank you. Let me just double check if there are any more questions. Yes. How do you deal? So this is a question from Sophia Stanley. Perhaps I missed this. How do you deal with the different dimensions of the estimates of B at different fidelity levels?
Okay, yes, I didn't mention it, but yes, for example, here in the different, we have two members on different fidelity level. They may not be on the same dimension. What we use is simply a prolongation, an interpolation of the coarser level onto the finest one, to be able to compare the different estimator. So you need to have an interpolation to go up to the finest level to be able to compare the different estimators.
Okay, very good. So, and there is one more question of Petayan, but it's not done. Oh, no, it's done now. So ENKS, beware, estimate B, just B H transpose and HB H transpose. Would that help in some way? So we never estimate. Okay, so good. In ENKF, we never estimate B, just BH transport and HBH transport. Would that help in some way? I think not, probably, but let's see what Jérémy says.
I don't know. In fact, I don't know. Yeah, we may think about that, but for now, I don't know if it will be best to estimate this HB HT. Yeah, just don't know. Maybe we'll think about it. And yeah.
If I may intervene, I am working with Jérémy on this. I'm not sure it would. And in practice, we are mostly interested in ensemble variational data assimilation. So based on on EDAs to generate ensemble members. And we don't focus on ENKF on the moment.
Okay, thank you. Thanks again. And we will now move to a next presentation.